Hello, this is the Fall 2018 Exam 1 for MA 165. Question 1, we are finding the domain of this function. So really all we have to care about is where the natural log of x is undefined. And that will occur for x less than or equal to 0, because really what the natural log will return is the power that you need to raise to get a certain value. You know, as that approaches, as that approaches, as x approaches infinity, the natural log will also approach infinity, and as x approaches 0, the natural log will approach negative infinity. So yeah, there is no power that you can raise to get a negative number, and so this is what we're dealing with here. So let's pull this thing out and set it equal to 0. 1 over 9 minus 1 over x minus 2 squared is, let's just say, less than or equal to 0. And when is this going to occur? Well, this term here would have to be larger than 1/9 or equal to it. When will that happen? Well, what if x is equal to -1? If we have -1 in here, we end up with -3 squared, so 1 over 9 minus 1/9. That will do it. So x is equal to -1 is an issue. What about something like x is equal to 0? Well, then we get 1/9 minus 1/4. That gives us something that we can. Oh, sorry. Yeah, sorry. I blanked for a second there. If x is equal to 0, then we have 1/9 minus something larger than 1/9, right? We have 1 over 4 in this case, which will give us a negative number. So, if we draw this on a number line, we know that x is equal to -1, and then some interval around or above x is equal to -1 is no good. But let's see what happens if we keep going up. Where will this thing evaluate to 9 again? What about x is equal to 5? There we will get 5 minus 3 squared. That will be 9 as well. So 5 there. So this is where things are undefined. As long as x is less than -1 or greater than 5, we're perfectly fine. If we plug in -2 here, we get 1/9 minus 1/16. That's a positive number. Let's plug in 7. We get 1 over 9 minus 1 over 25. That's still greater than 0. So really, the domain for this function is the entire number line minus this interval right here. And that's given by the union of the interval from -infinity to -1 and 5 to infinity. So there we go. And I gotta pull up the answer key for this exam just to make sure that we're doing the right thing. Okay, 1 is B. Question 2, let's consider this function defined on that interval, including 1, excluding 3 here for those endpoints. Choose the correct statement about the inverse function and its domain. So solving for the inverse of this function, we can rewrite this function as y is equal to x squared minus 2x. And we'll find our inverse by swapping all of our x's and y's. So we have x is equal to y squared minus 2y. Now this is a very easy point to get stuck at because it's kind of difficult to isolate y in this case. You can't really divide it out. You can't like separate the variables very easily. But what we can do is complete the square. So what if we add 1 to both sides? Add 1 to both sides. Well, then we can rewrite this right-hand side as y minus 1 squared. That will give us y squared minus 2y plus 1. And then on this side, we still have our x plus 1. Now if we take the square root of both sides, we get the square root of x plus 1 is equal to y minus 1. And let's see, let's just subtract, let's add 1 to both sides, and we end up with y is equal to 1 plus the square root of x plus 1. Now, what will the domain of our inverse function be? Well, the domain of our inverse is just the range of our original function. And the range of our original function will be given by plugging these guys in here. So we'll have the same kind of bounds. What happens when we plug in 1? We're getting 1 squared minus 2 times 1, so that gives us negative 1, and it includes that value, right? Because 1 is included here, so whatever we get when we plug 1 in will be inclusive. So we need a square bracket. And plugging in 3, we get 3 squared minus 6, which just gives us 3, and that is exclusive. We are excluding that 3 from our interval because 3 itself is not even in our domain. So there's there's the domain of our inverse, which is equal to the range of our original function. That gives us answer choice B for number 2. 3, compute the following limits. So whenever we see some rational, not rational, but a big square root expression, and subtracting or adding something else, what we're going to do is multiply by the conjugate of that expression. So that means we're taking the square root of x squared plus 4x minus x, and we are over 1, and we're multiplying that by not this thing right here, but its conjugate, which means taking this minus and turning it into a plus. So we have the square root of x squared plus 4x plus x, and then since we need to really just be multiplying by 1 here, that's the only legal operation that we can be doing, we'll need to do that on the bottom too, the square root of x squared plus 4 plus x. This will give us x squared plus 4x minus x squared over the square root of x squared plus 4 plus x. Our x squareds will cancel out on the top, and we are almost done here, because what we can do is divide everything by x, and you'll see why that's helpful. So we're dividing our numerator by x and everything in our denominator by x. We can factor this x into the square root by squaring it and putting that square root over everything. And what do we get here? We get 1 and 4 over x squared. This becomes a 1. This becomes a 4. Okay, so this expression is exactly equal to what we had over there. All the operations we've done haven't actually changed anything here. And now we can just plug in x is equal to infinity, because all we have here is a 4 over x squared. As x approaches infinity, 4 over x squared will approach 0. So the limit of this, as x approaches infinity, will be 4 over the square root of 1 plus 0 plus 1. That's 4 over 2, which is 2. So right now we are happy with C and D. What about 2? We're finding the limit as t approaches negative infinity of cosine of 2t times e to the t. Let's graph this right here, or just get an idea of what's going on. What happens to this part of our function as t approaches negative infinity? It will approach 0, right? Because e to the negative 100 is pretty small, and then e to the negative 10,000 is even smaller, so that approaches 0. It never goes negative, but it approaches 0 as t approaches negative infinity. What happens with cosine of 2t? Well, that's just always going to be oscillating back and forth. That really doesn't change. But because t is this part of our expression is approaching 0, so we'll get big oscillations here, which you'd think would be a problem, right? Because as t approaches negative infinity, if we still have this oscillating behavior going on, it's really hard to pick what value it's actually approaching. But because it's being multiplied by a smaller and smaller number, those oscillations will get infinitely small as t approaches negative infinity. And as a result, I hope you can see how this really just approaches zero, because if we're really close to negative infinity, we'll still be oscillating. If you zoomed in here, you would still see those oscillations. They are just infinitely small near negative infinity. So there we go. C is our answer for number 3. Number 4, solve the following equations for x. Okay, so properties of e and natural log is really what we're talking about here. If we add two natural logs with the same coefficient on them, so they both have a coefficient of 1, we can add those and just multiply their contents together under one natural log. So this is equal to the natural log of x times x minus 1, so x squared minus x, and that's equal to ln 6. Now we can take e raised to the power of both sides, and a lot of things will simplify out. We have x squared minus x is equal to 6. Now we can factor this as x minus 3, x plus 2 is equal to 0. This gives us roots of x is equal to 3 and negative 2. But there's an issue here. None of our answers include both of these guys. We see answers that include 3 but not negative 2. And why is that? Well, we know that the natural log function is only defined for values, real numbers greater than 0. So if we were to plug in negative 2, we would have the natural log of negative 2 plus the natural log of negative 3 is equal to 6. And while you could say that this kind of does work, because we can apply that same law, and we'll multiply these together. Negative 2 times negative 6. Negative 2 times negative 3. That just gives us ln 6 is equal to ln 6. That seems to work, but really we will be getting complex answers for both of these, which is we want to avoid that here. We're just dealing in the world of real numbers. So x is equal to 3 is the only solution that stays in the reals. So we are between A and B at this point. Now let's solve number 2. We have e to the 2x is equal to 2 to the third is 8, so 8 e to the negative x. What we can do is take the natural log of both sides. We will have the natural log of e to the 2x is equal to the natural log of 8 times e to the negative x. What can we do? What can we do here? Well, we know that the natural log of two things multiplied together is the same thing, just like the thing that we used up here is the same thing as the natural log of that first thing plus the natural log of that second thing. So we can split things off like that. Now let's raise e to the power. Actually, no, we don't have to raise e to the power of both sides. We are already good. We already did that. We already took the natural log of both sides. So things can simplify down. If we have the natural log of e raised to the something power, that's just going to be equal to that something. So 2x is equal to negative x plus ln 8. Simplifying this down, we have 3x is equal to ln 8, and dividing by 3 here is the same thing, because we're multiplying this by 1/3, it's the same thing as raising this 8 to the 1/3 power. And the cube root of 8 is 2. So ln 2 is our answer, and that gives us A for question number 4. I hope that whole thing made sense. And if any of those properties don't just come to mind when you're taking these questions, doing these questions, go watch a video, do some Khan Academy or something. They're all out there. Just Google them. Question 5. Consider the graph y is equal to x cubed. So let's graph that out before we do anything. It'll look something something vaguely like that. Find the equation of the graph that results from reflecting the original one around the line x equals 1. So here is x equals 1. What do we need to do to reflect it around that? Well, reflecting it will give us something like, nope, that's a little ugly, but I hope you see what I mean. So how are we going to take this first function? How are we going to take that first function and get there? Well, what comes to my mind is what if we shifted this thing? What if we shifted this thing 2 units to the right and then reflected it around itself? What would that look like? Well, it would give us exactly what we want, and I can't reflect a line on this page in this app very easily, but our distance between this function and x equals 1 at the origin, on the line y equals 0 is a distance of 1. So our reflected line, we want that to, whoops, that's a terrible x cubed. But we want it to be 1 unit away on the other side of x is equal to 1. So let's start this process by saying y is equal to x minus 2 to the third power. That will take this line and shift it 2 units to the right. Now the only thing that's left to do is to reflect it about itself, and all we have to do for that is to negate this whole thing. And factoring that negative sign in, we get y is equal to 2 minus x to the third power. That gives us c. And please, if what I was talking about shifting the thing and then reflecting it doesn't make sense, open up an actual grapher and graph these things. Graph the thing before we shifted it over. Before we shifted it over, after we shifted it, and after we reflected it, so you can really see what those changes are doing, because this graph is absolutely terrible. And I'm sorry about that. Question 6. Consider this function. Determine the values of a and b such that f is continuous everywhere. So this question is actually omitted on the answer key, and I'm guessing that's because there are multiple answers here that are actually correct. We are going to find the most obvious one and just move on, because I solved this and I did get an answer, and I'm pretty sure it is correct. Okay, so what are we dealing with here? We're dealing with a piecewise function, but where when x is less than or equal to 1, it's equal to this thing, and when x is greater than 1, it's equal to this thing. We want these two functions, let's say they have some arbitrary shape here, we want them to meet up using these a and b values. So we're pretty much shifting a and b around such that they connect there, and you can draw a line all the way through them without picking up your pen. That tells you that we've made continuous functions in the end. So really, these just have to evaluate to the same thing at x is equal to 1. But immediately the issue that we see is that when x is equal to 1, this thing is undefined. It has a denominator of 0. So we really want to get rid of that x minus 1, and the only way we're going to do that is by finding some value of a that allows us to factor the numerator and get rid of it. So what can we do? We need an x minus 1 factor on top, and since we don't have any, like this isn't a full quadratic expression, right? It's not x squared plus some amount of x plus some constant. We don't have any x's at all. So the only thing that's going to do that for us is this guy right here, right? Because we'll get x squared minus x plus x minus 1. And what that means is that a is equal to negative 1. We'll expand this out and get x squared minus 1 over x minus 1. So a is equal to negative 1. But this lets us cancel these two out, right? We will get 1. we will get, sorry, x plus 1 over 1, which is just x plus 1. Perfect. So what does this evaluate to at x is equal to 1? Well, we'll get a 2, and we can set that equal to this thing evaluated at x equals 1. We'll get 1 minus 3 plus b. This gives us 5 minus 1 is 4, so b is equal to 4. That gives us b as our answer. A is 1 and b is 4. And hope that entire process made a little bit of sense. Question 7, choose the right statement which describes all of the horizontal and vertical asymptotes of this function here. So looking for horizontal asymptotes, really what we care about is the limit as x approaches negative infinity of, and I'll call this f of x, and the limit as x approaches infinity of f of x. So what happens as x approaches negative infinity up here? Well, e to the x will approach 0, so will this e to the x, and we're really just left with 1 over negative 1. So this gives us a limit of negative 1. What if x approaches infinity? Then these two components will approach infinity equally quickly, and we don't really care about these constants. Those are nothing compared to the infinities we have over here, and the ratio between the numerator and the denominator is 1. You know, we have the same kind of growth happening on the top as we do on the bottom, so this ratio gives us a limit of 1. So we have, in the end, two horizontal asymptotes, one at y is equal to 1, and one at y is equal to negative 1. So we're happy with that. What about vertical asymptotes? Well, a vertical asymptote will occur when our denominator is equal to 0. And when will that happen? Well, we can set e to the x minus 1 equal to 0, e to the x is equal to 1. When is this true? Well, that's true when x is equal to 0. E to the 0 will give us 1. And there's our vertical asymptote at x is equal to 0. And you should graph this thing out too and take a look at what these things actually look like. It would probably be something like, I don't know, this is going to be ugly, but like that kind of thing. So you see we're approaching negative 1 as as t approaches negative infinity. We're approaching 1 as t approaches infinity, and at x is equal to 0, we have this vertical asymptote that they're also approaching. Okay, so that gives us D as our answer for 7. 8, if the sine of theta is negative 1/3 and we're dealing with thetas between pi and 3 pi over 2, what is cosine of theta? Well, on this interval here, our x values, our cosine, is always less than 0. So cosine must be less than 0. Let's keep track of that. Since we know that the sine of theta squared plus the cosine of theta squared is equal to 1, we can plug in sine squared and solve for cosine squared. So taking sine squared theta, we have 1 over 9 plus cosine squared theta is equal to, I'll rewrite that as 9 over 9. Subtracting this, we have 8 over 9. And taking the square root of both sides, we get plus or minus 2 times root 2 over 3. There we go. And since we know that our cosine must be less than 0, we will use the negative part of this plus or minus. And that gives us answer choice C for, no it doesn't. I just said we had the negative one. It gives us answer choice D for number 8. Question 9, from the intermediate value theorem, which of the following intervals can one conclude contains a root of this equation here? So let's set this whole thing equal to 0 and call it f of x. So we can rearrange this to say x cubed minus 2x minus 3 is equal to 0, and we'll say that this is f of x. Now what we can do is make a little table here with x and f of x, and let's try to find the interval on which this function goes from negative value to a positive value. Because really what we're dealing with here, if we graph this thing out, and this is not an accurate graph, but if we're finding a root for this thing, or this thing is equal to 3, and actually I think I can draw a better one. There we go. If we're finding a root for this, what we're really looking for is, okay, if this is x is equal to 1 and this is x is equal to 2, if it crosses 0, y is equal to 0 in between there, what we'll see is a negative y for the beginning of our interval and a positive y for the end of our interval. And that means that at some point, because our function is continuous in between, it must have gone through y is equal to 0. And so we can use that fact to our advantage. It looks like our answer choices are dealing with intervals between -2 and 3. So let's find all of these f of x values. Plugging in -2, we get -8 plus 4 minus 3, so that's -7 if I did my math correctly. Then plugging in -1, we get -1 plus 2, which is 1, minus 3 is -2. Plugging in 0, we get -3. Plugging in 1, we get 1 minus 2 is -1, minus 3 is -4. Plugging in 2, we get 8 minus 4 minus 3, that's 1. Wait, did I do that correctly? 8 minus 4 minus 3. Yep, I did. So take a look. At x is equal to 1, our function is below the x-axis, and at x is equal to 2, our function is above our x-axis. Since it's continuous in between, it must have passed through 0 at some point in between, and so our interval from 1 to 2 is our answer. That's D for number 9. Question 10, find the equation of the line tangent to that curve and perpendicular to this curve. Usually they ask this question and they want something tangent to a curve and parallel to a curve, so we have to take that into account. What is the slope of the line perpendicular to this curve? Well, this line's slope is -1/2. And if we want the slope of the line perpendicular, we have to take the opposite reciprocal of that. So we will negate this and raise it to the -1 power, and we end up with just 2. Okay, so we know that our line, in the end, has to have a slope of 2. That lets us get rid of option C, but not really anything else just yet. So this line is only going to be tangent to this curve when the slope of this curve is equal to 2. And you can kind of see that visually. If we have some function here and we have a line that we want to be tangent, look, the only place that that line will be tangent is where the slope of the curve we're trying to be tangent to is equal to the slope of that line. So let's figure out for what x values this curve has a slope of 2. For that, we will need the derivative of y. And in order to solve that, I'll rewrite this bit as -2x to the 1/2 power. We're going to apply the power rule. So that says that we can bring down the exponent of every x, multiply it by the coefficient that's attached to that x, and then decrement that exponent. So what that means is this will become 3 times 1 times x to the 1 minus 1th power minus 2 times 1/2 times x to the -1/2 power. And sorry, this is to the 1/2 power minus 1. So simplifying this down a bit, we have y prime is equal to 3 times x to the 0, which is just 1, minus x to the -1/2 power. Perfect. So we're looking for the solutions for this thing's slope, y prime, our derivative, is equal to 2. So 2 is equal to 3 minus x to the negative 1/2. Let's solve for x. And we can square both sides. Well, you know, okay, we're squaring both sides and then multiplying, or taking each side to the negative second power. Actually, 1 to the negative 2 is equal to x times negative 1/2 times negative 2. That gives us x to the first and 1. So this has solutions for x is equal to 1. At x is equal to 1, what is the y value of this function here? We'll need that for our point slope form of our line that we eventually write out, because we know this is our x value for our point slope form. We only need one more value here. So let's plug that x in. Y is equal to 3 minus 2 times the square root of 1. That's 3 minus 2, which is just 1. So y is equal to 1 at that point as well. So point slope form time, we have y minus y0 is equal to m, our slope, times x minus x0. Plugging these things in, y minus 1 is equal to 2, the slope that we found at the very beginning, times x minus 1. This gives us y is equal to 2x minus 1. That is option D for number 10. Question 11. Suppose we have a function f of x such that f prime at 2 is equal to 7. Evaluate this limit. So it's been a long time since I did Calc 1, and I have absolutely no idea what they're really talking about down here. And the nice thing about this question is that you don't have to care either, because what we can do is find a function that works for this. What is a function that has a slope of 7 at x is equal to 2? Well, that's just, why not just y is equal to 7x? That has a slope of 7 no matter what x value you plug in there. And so what we can do here is we can compose our functions with 2 plus 3h and 2 minus h divided by 5h, and this problem will become incredibly easy incredibly quickly. This will be the limit as h approaches 0 of f of 2 plus 3h, so that's 7, and then we replace that x with 2 plus 3h, minus 7 times 2 minus h over 5h. This is the same thing as 14 plus 21h minus 14 plus 7h over 5h. This gives us 28h over 5h, or just 28 over 5. As h approaches 0, well, we don't care because there are no h's left, and we end up with 28 over 5. That's C for number 11. How many solutions on the interval from 0 to 5 pi over 6 are there for this equation here? So we're going to be using two identities for this. That the tangent of x is equal to the sine of x over the cosine of x, and also that the sine of 2x is equal to 2 sine x cosine x. Let's rewrite this equation then. We have sine x over cosine x is equal to 2 sine x cosine x. Let's multiply both sides by cosine of x. That just gives us sine x is equal to 2 sine x cosine squared x. Let's subtract this, let's subtract this sine x over here. We will get 0 is equal to 2 sine x cosine squared x minus sine x. Let's factor out a sine x on the right side. So 0, and I'll actually rearrange this so it's on the left. So sine x is equal to, sine x multiplied by 2 cosine squared x minus 1 is equal to 0. So this will be true whenever sine x is equal to 0 or 2 cosine squared x minus 1 is equal to 0. Let's rewrite this as the cosine squared of x is equal to 1/2, and take the square root of both sides, we end up with plus or minus the square root of 1 over 2. That's the square root of, well, it's 1 over the square root of 2, which you can rewrite as root 2 over 2. Okay, so when is this true? Let's make a unit circle. We know that we're dealing with all of the thetas before 5 pi over 6. Well, sine x will be equal to 0 where? Well, y is equal to 0 at, this works for theta is equal to 0, and where is cosine x either root 2 over 2 or negative root 2 over 2? Well, that will occur at pi over 4 and 3 pi over 4. And so there we go. We have 3 different points where this function evaluates to 0, and so that will also make this function work up there as well. That is answer choice C for number 12, and we are done.